Greetings and welcome to our first session in Math and Graphics for Computer Games, Term 1. I'm Frederick and it's a pleasure to start this new year with you. I'll briefly go over the initial data that's on the learn.gold page for us. So make sure you have access to this page. You should. If not, please get in touch with me and we can check how to enroll you on that page if you're not already there. My email, which is probably the best way to reach me, is ffl@gold.ac.uk, and you have it here at the top of the page. So there is already quite a bit of info that's available on the page, and I will keep adding to it during the term. You'll find a description in particular of how we assess your work and your study during the term. So it's essentially two main courseworks, and there are details in there, but the first one will be an individual project around procedural graphics. I'll say a little more in a few minutes. And then the second one towards the end of term will be a group project where you create a team of 2 or 3 people ideally, with comrades in your class. And that final project for this term is usually open to pick up a topic that we've covered during the term. It could be a mixture of topics as well. But we'll talk more about that later, and I'm sure you'll have questions during the term about these projects, and then please indeed do contact me. So initially I recommend that you contact me by email so we make sure that things are running smoothly, because we will do most of our contacts online, if not all of it. Unfortunately, because of pandemic and restriction on the rooms available on campus, some courses like this one are provided essentially online. However, I plan and hope that we can set some informal meetings and perhaps find time to all get together a couple of times during the term, or maybe at the very end after Christmas when you submit your final project. Maybe we could try to find a room and have final presentations. We'll see how it goes. Yes, okay, so if I browse through rapidly, you'll find a lot of information at the top of the page. Spend some time on the recommended book. So for this term, there is one excellent book that is actually, since this year, has been made fully available online for free by the authors. It's a book that in its second edition was published about 10 years ago, actually, almost to the day. And I've been using that material since then, and refine it a bit over the years, so that the material that's in that book covers a large part of what we see during the term. There's a few things that are not in the book that we will talk about and study and work on. Actually, the procedural graphics first project is not covered in this book, but most of the other material we see is in the book, and it's very well done, as you I hope you'll see. You can tell me, please give me feedback, but it's been criticized in positive ways over the years by a number of people in the academic teaching games, math, and also in the industry. And the authors are linked to industry, so they have experience building games as well. There is a second book. And by the way, there's a few links you'll see where you could get the book if you really like it yourself. There's some copies in the library at Goldsmiths. There's also online access via the library, but now, as I mentioned, since earlier this year, you have a website listed here, gamemath.com, which has all the content of the book available. So that's great for us. So you'll see, especially the first few weeks, we'll cover material taken from the book, and I'm sure you'll find useful to go back to the online version as well, where you'll see more descriptions of the material we see. So one thing about that book is that it's a bit unusual in the sense that if you look at typical textbooks, there's usually a lot of material in a sort of compact way, lots of equations, exercises, etc. It's a lot of focus on the details. Here in this book it's a mixture, so you have details, but you also have lots of narratives, lots of discussions of how this content, these methods, this math is used in a game context or in a programming of graphics context. So in that sense, the book is really worth spending time on. And in the lectures, I will mention some of the details, but not as much as what's in the book. So it's actually a good read to go to after or even before our lectures. Yes, there's a second book, also recommended, published around the same time, in its third edition then, also by a well-known person in the field, in both teaching and active in making games, Eric Langill. He has a few other books around. I think he has one on physics for games as well. So that book is a bit more traditional and it has more content. So if you look at that book, you'll see that it covers more material than the other one, but it has much less on the narrative and sort of experience side. So these two books can be seen as sort of complementary to each other, and some of the topics not covered in the first book can be found in that second book. So it's an additional reference, but not the main one we will use. So for this first week, we'll start going into the real content, and now I'll just give you another brief overview of what we do during the term, and that's the slides that you see here, slides intro, and that will be the end of this short video, and then I'll come back with a second recording where we'll start looking at some of the content from following the book at the beginning at least. We'll be looking at some of the basics, just as sort of a refresher, probably for most of you. And later on, we'll be ready for more advanced material, of course. We'll spend at least a week, probably some of next week, on vectors as sort of the first major topic that's used in computer graphics and games programming all the time. Okay, so let's look at these slides. Slides again that you find here at the top, slides intro. So, right, let me see here. Okay, so what will we see? Today we'll spend some time later on in the second video on what is in the book, I think, chapter 1, and it's about sort of review of basics, in particular coordinates and coordinate systems. So how do we organize space? In graphics, in games, we want to be manipulating objects, and we want to have good notions of where to put them in a space, how to move them, how to animate them, etc. So the basic topic we need to bring into play is systems of coordinates, and there's some subtleties, especially in 3D, about how we go after that. And then we'll see a few other things, including trigonometry. So trigonometry is all about cosines and sines. This may ring a bell. Anyway, we'll do a review on that, and there's also some additional video. Then we'll move on to, as I just said before, vectors, and we'll see vectors we'll focus on vectors in 2D problems in the plane or in image surface, and in 3D in a volume. And you have an example here on the right of what we mean by a vector. So literally a vector is an arrow with an arrowhead, so it has a tip and it has a sort of a start. So it's oriented, it's an object that has an orientation, and it has a length. And we use that object, mathematically speaking, for things like tasks like specifying the position of an object, for example, or simply a position in space that we want to reach. Orientation, so the vector also carries that kind of information. We can also do measurements, metrics, so how far is one object to another, measuring distances between objects or parts, etc. So vectors are very useful in many, many ways. Just to give you a hint where this will appear again a lot, it's not just about objects, but for example, if we think of light, how do we manipulate and represent light? We will think of light via, in particular, via vectors. So an arrow will indicate where the light is going, shining, hitting and intersecting with objects, mirrors, etc. So vectors will play a big role in that context of light rendering. By the way, light rendering is a topic we cover typically in the math part 2, so in after Christmas, if you take the term 2 option. In the context of vectors, so this is where maybe for some of you we will see new topics. We will talk about dot products and cross products. So these are the idea of multiplication that you're all familiar with, multiplication of numbers. And we have a equivalent notion. Actually, we have two notions when we think of vectors. So we can actually have a concept of multiplying a vector by another vector. And the two forms of that, the two flavors, are so-called dot product, sometimes called scalar product, essentially because you multiply two vectors in this particular way, and the answer is not a vector, but it's a number or a scalar. And then there is this other type of product where you also multiply two vectors, but then you get a new third vector. We call that the cross product, sometimes vector product, also it's called. Right, so that will be at least 1 week, perhaps a little more. Then we'll move on to another interesting type of objects used all the time in programming for games and graphics in particular, but not only. Also used in machine learning, for example, and optimization, all kinds of places. The concept of matrices. Matrices, what are they? They're really a notion of gathering together in tables 2D arrays, 2D boxes if you want, and you put a lot of numbers in there, and you carry these with you around, and these numbers can be used for all kinds of applications. So here you have some examples. You see A and B are two matrices, 3 by 3 we would say, that is there are 3 rows and 3 columns. So 3 by 3 meaning they have 9 slots, 9 numbers in there. You could have variables as well in there. You could use matrices not only to carry numbers, but actually concepts or variables. We'll see examples much later. And then we can multiply matrices, like we introduce notions of multiplying vectors. We'll look at how can you multiply these objects, these matrices. So we'll see the basic of matrices. There's more possibilities there, more details, so we spend a bit more time there than with vectors. And that later, this notion of matrix turns out to be very important because it's the basic concept to carry on particular transformations that are used in graphics, again, so-called linear transforms. And just to give you flavor what we mean, well, linear transforms will be things like rotations. So you want to rotate an object in a 3D space or a 2D space. How can you do that very efficiently? Well, we have this notion of matrices here. So a compact sort of set of numbers that you can apply in particular on a vector, and it will rotate the vector the way you want it. We can do things like scalings, we can do mirror images, and a few more things with these linear transforms represented by matrices. Okay, so we'll dive into that. That will really get us going into this world of what kind of mathematics is useful for graphics and games programming. So we'll see other things like, again, if you've never seen matrices in details, these will be new, but there's nothing too mysterious. They always relate, these notions that we list here, they always relate to very practical graphical effects that are useful to us. So we'll have a notion of determinant, which is a particular feature of a matrix, and will reveal to us certain aspects of what that matrix can be used for. There will be a notion of an inverse of a matrix, so a companion matrix, which basically does the opposite of your initial matrix. So if you think of a rotation of a certain angle in 3D, right? So in 3D rotations are more complicated because you can do rotation in 3 axes. One matrix can allow you to do such a rotation along 3 axes at once. That's one of the reasons it's so useful. And then you can also compute, there are ways to compute an inverse, so to do the opposite, to go back to your original position all at once. There'll be notion of orthogonality, so these are special matrices that have nice properties. We'll look at those. Notion of homogeneous matrices, so this is actually an extension of matrices where we can do more than just linear transforms. We can combine the linear transforms, such as rotation, scalings, with additional manipulations. And we'll see a few of those, and one of them will be how to do perspective projection. Perspective projection is how we create an image from a view out there going through a single opening. So you can think of your eye, you have a pupil, and that's your opening, and there's light coming from outside, bringing information, going to that little hole, and then it goes to the back of your eye on a almost flat screen. So it's very much like it's a camera. It's the concept of a camera, and that kind of projection of the information through a single focal point creates on the other side an image, a version of what's out there, and we call this projection a perspective projection. So matrices again will play a role there in creating and understanding and changing these types of projections. So very useful, obviously, if you have a 3D world and you want to create a view with a virtual camera, a new image from somewhere over here, and then you want to create another one from somewhere over there, you can use this notion of perspective projection. We'll actually return then to rotations in 3D, because it turns out that first it's one of the most used transformation in computer graphics and games. We do 3D rotations all the time. It's a more subtle and complex transformation than just doing translations. So translations is a trivial thing to do. You move along a vector, and then you want to go to another place, you move along another vector. So in order to understand and do this kind of transformation, it's very easy. But to do rotations is much more involved. And in our bag of tools to carry on rotations in graphics, in computing, we have more than one way of doing this. So we will have seen by then the way of doing rotations in 3D with matrices, of course, but then we'll look at a few other very popular ways, and each of them, such as Euler angles, will have its own advantages and disadvantages, and that will be why we introduce these things. And it won't be just theoretical for your knowledge, but actually you'll see that in the world of graphics programming and games programming, these different ways of processing 3D rotations are used. They're used today, they've been used in the past, and it's because each of them has its own advantages and some disadvantages, so they don't overlap completely. So there's no one of these that's completely the sort of the best at everything. Each of them is the best at certain types of applications. One of them that is more probably new for most of you. Usually I find almost all the students haven't encountered this notion, quaternions, unless perhaps you've already done some more advanced games programming. Quaternions are a notion of extending complex numbers. So some of you probably remember complex numbers. Complex numbers is a real number with what's called an imaginary number. Imaginary means that your usual notion of a number is multiplied by the square root of a negative. So you probably remember that square root of a number, usually you have a rule that you can only compute the square root of a positive number, and that gives you some answer. An answer which, if you square it, you get back the number under the square root. Okay, that's the basics of square roots. But mathematicians a while back now, a few hundred years ago actually, extended this notion of square root so that you would allow to have a negative number, but that would be a different kind of number than our usual real numbers, and we call these imaginary. And together with real numbers, if you bring the two together, you get this notion of complex number. We will look at that, don't worry about that. It's really a way of extending the type of number systems that we have in our bag of tools, and it allows us to do certain things much more efficiently than if we didn't have these tools. Complex numbers are very useful also to do, in our case, 2D rotations. So we will see a connection between using these for 2D rotations. And the equivalent for 3D rotations will be these quaternions. They're called quaternions, so they have imaginary numbers involved as well, and real numbers. And quater here should evoke the notion of 4. So it's actually a vector which has 4 slots, 4 dimensions. And that's used for, in particular in our case, 3D transformations, 3D rotations. Again, don't worry too much about these things if it's completely new. You'll see it's really interesting. And there's plenty of examples of how to use these things, tutorials as well that I will provide, in addition of what we see in the lectures, and programming code, if you want examples as well. So we'll get familiar with these. And by the end of term, you should be familiar with all these notions, and they will sort of be part of you if you go into the world of games programming later, professionally speaking, and graphics, as they are used again all the time. Let's keep going. So this topic, we will also spend some time on that topic, so-called L systems, or Lindenmayer systems, and this is a way of producing graphical objects, which sometimes goes on under the more generic term of procedural graphics. So all kinds of algorithmic methods that are used in computer graphics to create lots of content or lots of assets being sort of an equivalent term in the world of games. And we will, as an introduction to this type of processing, we will spend time in particular on L systems, very famous type of procedural graphics that has been around for decades now, and in the world of games has been especially used to create vegetation and trees. And you see some examples here on the right. It's also a kind of technique that can be used to create city maps rapidly. So basically you have an algorithm that can create very, very rapidly in real time an entire city. So we'll see how this is done. And our first coursework, first project will be to use this kind of technology for you to do a project where you actually create, you use this idea to create different types of trees in particular. So why is that useful? So imagine you're creating a game and you want to have a forest, and you want to have a forest that looks realistic. So you would like each tree perhaps to be unique, which is the case in reality. it would be very inefficient if you had to do all this by using, let's say, 3D Studio Max or another graphics platform. So is there other ways of doing that? Well, procedural graphics technology and L systems in particular is a way that allows you to do this automatically. And then you could even go back to the trees and then start modifying them, let's say in 3D Studio Max, for example, if you want a tree to have very particular features. But the technology itself, L systems, allows you to rapidly get your entire forest. Okay, so hopefully that sort of justifies why we spent time on that. And there are, just to give you a flavor of what else there is in the world of procedural graphics, so another related technology which appeared also decades ago, around the same time as L systems, is so-called fractals. You may have heard of the term fractals, you may have encountered them. In the early days of fractals, in the 1980s, 1990s, they were particularly used to create these landscapes. So this is an example. So if you wanted to create such a landscape back then, before using the concept of fractal, you'd have to actually sort of edit and do partly sort of interactively create a landscape, a mountainscape, a surface, and add details, and it could be a very involved process. But fractals is one way of thinking of how to modify equations so that they create a lot of complexity, a lot of have a behavior of the outcome of the algorithm that starts with a flat surface and rapidly create versions of these surfaces over iterations, which introduce lots and lots of details. So if we were to zoom here, we'll see that this region has lots and lots of details, and the kind of details that you see there, you can think of it as a sort of texture. Well, they're similar to the texture you have there. That relates to this notion of a fractal. And in nature, turns out that this kind of behavior is also observed. So this way of thinking of processing initially very smooth objects and making them very non-smooth also has a relation with what we observe in nature. And then it's also used to to produce all kinds of visual effects. So you have some examples here, very involved and beautiful effects, which would be hard to create otherwise if you didn't have this kind of technology. Okay, so we'll have a look at these. So overall, as I mentioned earlier on, over the term, you'll have two main projects. First one will be usually set around midterm, so sometime around the end of October, probably. We'll set that up, and usually will be due, depending when we set it up, perhaps the end of November or something of that sort. And this is an individual project, so each one of you will explore this as your first project. There's already an example and some details on the learn.gold page, so you can also check that if you're curious how this goes. And then the last project, second project of term, will be again a team project, 2 or 3 people working together, and you select a topic, or you can come up with you propose to me an idea that uses some of the techniques, or one technique if you prefer, or a combination that we have studied during the term. So here's an example. It could be let's explore using quaternions in a particular type of application. Could be, for example, animation. You'll see that quaternions are in particular used to create many frames when you move an object in 3D, such that you have a very smooth animation. That's one of their main advantage. So that's about more or less all we will see during this term. And next term we will see, just to give you a flavor, what comes after. Sometimes we start covering some of these topics at the end of this term, depending how quickly we go. So one of the big topic is interpolation, and this is basically the idea of how do you relate data points to create different graphical objects. So in our case, we'll be interested in how to create curves, all kinds of curves, in 2D or 3D, and then create all kinds of surfaces, also in this time in 3D. And we'll see topics like splines and Bezier way of interpolating data, and a few other methods, but these are some of the most well-known, popular. In the world of surfaces, we'll also spend time on NURBS. Don't worry, this is an acronym, so basically it's a non-uniform rational B-spline, so it's related to these notions of how to interpolate curves, and it's applied to create surfaces. We'll spend also time on meshes. So meshes are surfaces which are discrete, so rather than have mathematical objects that are curving through the data, we put a lot of planar objects, usually triangles or quadrangles, so squares or rectangles, that connect all the data points. And if you have this notion, then we'll see, okay, what can we do with that? How do we manipulate this? Can we change the resolution, etc.? These kinds of issues. So we spend time on basically how to create nice looking sophisticated curves and surfaces. Then another big section of term 2 is light rendering. So I've mentioned a little bit that before. In light rendering, we will use vectors in particular. We will model how to model light, so a light beam, let's say, coming from a light source, and how is it interacting with objects. So, for example, the surfaces we will have studied just before. Sorry. And how can we bring in color? How can we bring in effects due to changing the material properties, transparency, fluids like water, what happened to light when it goes to water, etc., or other materials, other liquids. Yes, materials, for example, are represented by these acronyms here. BRDF is an acronym for bidirectional reflectance distribution function. So, it should evoke that it relates to light. Reflectance means how the material is reflecting light. Distribution means that it's reflecting light, but not necessarily the same way for every angle. And this is where different material reflect light differently, and in particular differently depending where you put the light beam and where you put your eye or camera. Towards the end of term, we also usually start looking at we go more into physics, and we look in particular at fluids, so that we could understand and do more sophisticated effects like smoke, different kinds of fluids, fire, all these kinds of effects, and have a good grasp, good understanding, and actually reproduce these effects. And in the context of all these topics, there's a few refresher we do. One in particular is on differential geometry. So this is notions like nothing too sophisticated, but it's good to do these refreshers, usually I find. So we'll see notions of, for example, how do we represent and compute curvature of a curve, curvature of a surface in particular. Okay, so yeah, that covers. Give you again a more detailed overview of this term, and also some hints on what you could study if you take term 2. The main way again to contact me is my email, so ffl at gold.ac.uk. The learn.gold page here will be your main other resource. You can also find me and see what else we do, for example, like research projects at the level of postgraduate studies with PhDs, etc., or other researchers. Usually nowadays I put that kind of information on my LinkedIn page, so you can look me up on LinkedIn. Just search for my family name. I think I'm about the only one with that family name. And there's also, I invite you to look, or you can ask me if you don't find it, there's a group for the MSc Computer Games Programming that we've created a few years ago, so you'll find We put some generic information there, but also it's a way to stay in touch and get in touch with alumni, people who've already done the course, graduated. There's also a few people who are from the industry in there. I think most of the lecturers are also on that group, so it's a good place to reach out to other people and also see some additional information that we put there. And I invite you, if you join that group, to yourself use the group, and you can put information there when you see interesting things relevant to the computer games world. And some of you, of course, are taking the VR, MSc, AR, VR, XR. Some of you are auditing the course, and you may be coming from another master's project. So you're welcome to join that group as well, of course. And by the way, the field of virtual reality and graphics very closely related to computer games. So although I tend to emphasize computer games as an application, everything we say is really more general because it applies to all kinds of disciplines related to computer graphics. So VR, AR is definitely an emerging area, and of course it intersects with games as well. But there are even other areas such as special effects for films and video, and we could mention applications in the advertising industry, on the graphic side, and also on the scientific side, scientific visualization, interactive visualization of data, for example, of all kinds. For example, we do work a lot in the biomolecular area with collaborators who are specialists in different subfields of biomolecular science. So things like genetics, DNA, RNA, for example. And there we apply, well, basically all these notions that we see in this course in that context. So yes, so please, if you're on the VR side or coming from other fields in this course, I invite you to join that group and be active and participate. So thanks again, and I'll see you shortly in a second video where we will start looking at some of the basic math that we need to cover. Goodbye, thank you.